Good day, viewers. Welcome to Cayman Faces tutorial. And today I'm going to be teaching you a very short concept of how to prove the centripetal force. This mostly applies to physics students and then science students that really needs to know how to prove the centripetal force. Shortly, what is the centripetal force? The centripetal force is the rate of change of a tangential velocity. So when we are talking about that, we talk about a body can be rotating and can be cycling about in a circular motion. When you have a ball or an object or a mass or a person or a cyclist going about in a circular motion, that type of force, the net force of that particular body is what we defined as a centripetal force. So in short, you can say the net force causing the centripetal acceleration of an object in a circular motion is what we refer to as centripetal force, right? So in another concept, we also define the centripetal force as a type of force that keep its direction towards the center of that circular path. I repeat that it's the type of motion that keeps its motion, or that keeps the direction of the force towards the center of that particular path, and which we always say it is perpendicular to the velocity of the body. The centripetal force is always perpendicular to the velocity of the body rotating around that particular path. So we usually refer to it as an inward force, because it's a type of force that keeps that body towards the center of that cycling or of that motion. So now today I'm going to give you a very short proof of how to prove that centripetal force. I'm bringing these short proofs. After this proof, I'm going to show you more and more and more. So let's get to the business. Now that you know what centripetal force is, this is a small diagram showing you what centripetal force looks like, right? This is a circular path that shows you, probably I've labeled this O, A, and B, right? I labeled that O, A, B, and then I also have this as P, Q, and S. P, Q, and S. P, Q, S is here. So I actually enlarged this to be something like this, which is that when the body is rotating about that particular circular path, the net force is what we are going to be looking at. And I just told you now, don't forget that that centripetal force is towards the center. Is an inward force. It's towards the center of the circular part or of the circle, and it's always perpendicular to the velocity of that body. It's always perpendicular to the velocity of that particular body. Don't forget that. Always perpendicular to the velocity of that particular body. You can see it's always perpendicular to the velocity of that particular body. So what do we say? I've just take this, what is happening here, to be an enlarged part of this place, right? So let's quickly go to the business. How do you prove it? We all know that a classical force we know here is F is equals to ma, right? F is equals to ma. So, but we are not quickly going to this first. We will first prove the A, which we are going to take here as the centripetal. We are going to take that one here as the centripetal acceleration. Right. That is what we are going to take the A. So once we are able to prove that A as the centripetal acceleration, then we can quickly go ahead to substitute that A into this place, and we'll be able to get what the centripetal force will look like. So if you look at this triangle, the one at the right, you will realize that something is happening here. The directions are different. This one is towards here, this one is towards here, and the other one is towards there. Then if you see that mathematically, you can see that the PQ here, if you add it to this, it will give us this, because this is like the resultant. If you look at it, that is like the resultant. So let's quickly put that out. We can say that the PQ, which is a vector, plus if you add it to the QS, which is also a vector, will give us PS, which is also a vector. If you look at that, what I've just done here is to show you how this plus this will give us what is happening as the resultant, which is that blue, the tangential velocity of that particular motion, which is the blue, the one in blue color of what you are saying. So, and you know they have been able to give us what is going to look like. This is going to be a vector minus v1. This is going to be v2. Then it's going to give us the change in velocity. So if you bring that together as well, you are going to have, say you are going to have the PQ is going to give us minus v1, right? There is other one is going to give us v2, which is going to give us a change in v. If you look at it, I've just brought this out, this, and this, right? So you are also going to have this. So if you rearrange this, you are going to have, if you arrange that, you are going to have change in v now to give us v2 minus v1. It's just a matter of rearranging this. You are going to have this, right? So you are going to have something like that, right? So this is what you are going to have for the change in velocity that you are actually seeing. That is how to prove this out. So after that, you quickly go ahead to talk about what is actually happening. What is the similarity? These two triangles here are the same. You can take them as the same. So you can say, you can call the one at the right hand side and the left hand side, you can make them to be similar. So you can actually bring up something with that and say, since triangle PQX and the triangle AOB are similar, right? So if you look at it very well, you see they are similar. So what do we want to extract out from these two triangles? What we want to extract out is we want to be able to see how the velocity is going to relate with their radius. Because now if you compare this with what is happening here, you see that most of the places we have the velocity here, inside of that particular circle is constant. So that's why this is actually a constant velocity that we are going to be having. This is a constant velocity. So it's going to be replaced by the radius. So what am I saying in essence? What I'm saying in essence is that the change, if you compare this change in V, which will be, this change in V will be compared to the AB. So you can say so from there, we can say that the change in the V, we have just proved now, if we divide it by the AB, I'm going to show you that so you know what I'm doing. What I'm saying here is that the change in V here, if you compare it with the resultant we are going to be having here, if we take it as the resultant, that is the place we are actually going to have, that is where you are going to have a curved part. That is where you are going to have a curved part in this one now, right? Which has been made linear. So if you say that, if you compare it now, what are we going to have from there? The change in V can just be simply taken as V. That change in V is supposed to give us V2, right? Supposed to give us V2, or you say V1. Let's take that one as V. Let's just take it as velocity divided by, right? What is the AB going to give us there? Wherever what is constant here is the radius. The constant here is you have this radius. Then what is constant here is the velocity. So that's what we are saying. What is constant in there? The radius. Then what is constant in the triangle AOB is there is the radius, which we take as r. This is what we are going to have, right? So that's what we are going to have. So now that is what we are going to use. Don't forget that AB itself is a particular arc. It's a arc here. AB is a arc. If you check it, that AB is going to be a arc. If you look at it, it's going to be a arc. So what we are going to be taking there, that's going to be a arc, but we are taking as a constant speed. But you are going to treat that place as if it's a arc, right? Because others are radius and they are constant. So you are going to take it as a arc, and you know what that is. So we are just going to write here and say that since AB is an arc, right? So this is an arc. What is going to be what is going to be our answer for that? What is going to be our answer coming out from that particular place? We are going to take it as a distance. That's what we are going to be taking it. You will take it as if it's a distance walked. You will not take it as constant. You will take it as a distance walked, as a distance traveled, or a distance covered. So AB will be distance covered. So, and you know what distance is? We can say AB, we can take it as S. Or let me say change in the S. Right. We can say change in the S so that the distance is changing. So we not just have so the distance is changing over time throughout that particular curved path. Right? So from there, what is that going to give us? You know what this displacement is going to give us? It's going to give us velocity times time. So therefore, that AB is going to give us V change in time. Right. So since the displacement is changing, the time will also be changing as a result. So having gotten all these things, you can put, since you have gotten this as well, you can put that in red into what you have gotten here already. You can put that one into this place. Because now if you look at it, we are able to talk about the triangle here. We prove what is change in V. Then we talk about what the similarity between the AOB, triangle AOB, which we pulled out, triangle AOB in the circular part, and the triangle PQS, in what we pull in triangle we pulled out. So if the two now can be, you can put this into this place, because now we know what AB is. So if you put that into there, you are going to have, therefore, if you substitute, you are going to have change in V all over V change in T is going to give us V over R. You already have V here over R, and that is what we have here, V over R. This place you have change in V, then I put change in V here. It is because AB here is turning to, and that's why I represent it by V change in T, right? So if you look at it very well, you will see that we can actually like cross multiply some few things here. If you cross multiply a few things here, the change in V over change in T can be V squared over R. And you know what that is? Since change in V over change in T is equals to the acceleration. It's a normal classical acceleration. So therefore, we can say that A is equals to V squared over R. Yeah, we can say that. A equals to V squared over R. Yeah. So this is what we call the centripetal acceleration. Centripetal acceleration. You have to get the centripetal acceleration first. Acceleration. Right. So don't forget what I told you from the beginning, that F equals to ma, which we all know. If you check from the beginning, F equals to ma in equation 1, you can make this as equation 2. Right? You can make this as equation 2. So if you substitute 2 into 1, so you will call that F is equals to ma, right? So F here is going to give us m. Now our A is V squared over R. So F is the centripetal force here, because the A is now representing the centripetal acceleration. So F will be centripetal force. So therefore, that F we are looking for is going to give us m V squared over R. That's what it's going to give us. M V squared over R. Right. This is going to be our final answer. And the centripetal force is going to be mv squared over R. So you will see that this is the same formula that you have been seeing, F equals to mv squared over R in your textbook, in your classes, and then you don't know how to prove that centripetal force. This is how to prove the centripetal force, by first going to the centripetal, noting what the centripetal force is, F equals to ma. You will resolve what is the change in velocity. You are going to have this. From there, you compare the angle PQS and the AOB together, you will get this. And from there, you will treat AB as an arc. That is, the AB is going to be distance covered, which is going to be a change in displacement. And then you introduce the formula for change in displacement. You replace it back there, and then you have this. When you cross multiply, automatically this return to the acceleration. Then that is referred to as centripetal acceleration. Since F equals to ma, you can replace that back into the acceleration. Then you have F equals to mv squared over R. This is a formula that everybody have been using, but most people don't know how to prove it. Follow my channel, subscribe to my channel, and then follow my pages, K-Man Physics Tutorial, for more of this particular proof. I'll be dropping more proofs, physics proofs, mathematical proofs, to show you simple way of how to show you prove all the physics formulas that you have been saying before. Subscribe to my channel. See you in the next video. Thank you.